Applied Behavior Analysis, or ABA, operates on a strict scientific mandate. The goal of this field is to improve socially significant behavior. But observing a change is insufficient. A behavior analyst must empirically prove exactly why that behavior changed. This requirement is known as the analytic mandate. It forces the practitioner to step away from passive observation and engage in active, controlled experimentation. We can visualize this experimental approach through a core mathematical concept, the equation y equals f of x. In this model, the letter y represents the dependent variable, or dv. This is the specific, measurable behavior we are observing to see if it changes. The letter x represents the independent variable, or iv. This is the environmental condition or specific clinical intervention that the researcher systematically manipulates. Behavior analysts operate on the assumption of determinism. Variability in human action is not random. It is an effect directly driven by manipulations of the external environment. To apply this in a clinical setting, we have to define our variables strictly. The dependent variable is always the responder. It is the target event you measure to see if your environmental manipulation actually worked. On this screen, the left column shows clinical examples of a dependent variable. You might measure a client's rate of aggression, duration of on-task behavior, or the frequency of their MANs, a behavioral term for requests. The independent variable is the exact opposite. It is the doer. This is the specific agent of change that the practitioner introduces, withdraws, or alters on purpose. The right column shows the independent variables. These are the tools of intervention, like implementing a token economy, using differential reinforcement to reward alternative behaviors, or introducing new visual supports to a classroom. A frequent error in practice is confusing the two, such as mistaking a client's action for the intervention itself. Another error is labeling the general environment as a variable. A classroom setting only functions as an independent variable if the analyst actively changes a specific element within it. Experimental design requires the practitioner to explicitly control the independent variable while strictly measuring the dependent variable to document the resulting effect. Identifying your variables is only the first step. If the variables are not precisely quantified, the mathematical relationship between the intervention and the behavior breaks down completely. The dependent variable requires an operational definition. This means defining the behavior entirely in objective terms based on its observable physical shape or topography, rather than guessing at internal subjective states. Vague labels guarantee unreliable data. Defining a target behavior loosely risks definitional drift, where multiple observers gradually score the exact same actions differently over time. The independent variable demands equal precision. In behavior analysis, this is treatment integrity. Every intervention constitutes a strict step-by-step procedural checklist that must be executed identically every time. If staff implement an intervention inconsistently, you lose the ability to attribute any changes in the target behavior to your planned manipulation. Integrity failures lead to two severe errors. A type 1 error is a false positive, where an ineffective intervention looks successful due to some unmeasured fluke in delivery. A type 2 error is a false negative, where a highly effective procedure fails simply because it was executed poorly. Without a rigorous operational definition and strict treatment integrity, the data collected is scientifically invalid. The experiment fails before it even begins. Clinical environments are dynamic spaces filled with uncontrolled background noise. These ever-present background factors, fluctuations in lighting, the time of day, a sudden change in staff, or a client's minor illness, are known as extraneous variables. An extraneous variable is mostly harmless until it crosses a critical threshold. If left uncontrolled, it morphs into a confounding variable. A confounding variable systematically changes at the exact same time as your intervention. Because they co-vary, the confound provides a highly plausible alternative explanation for why the behavior changed. Common confounds in applied settings include maturation, natural developmental changes in the client over time, or history effects, such as a new medication prescribed by a doctor outside of the clinic. Confounding variables destroy a study's internal validity. Once they enter the equation, separating the true effect of your intervention from the chaos of the environment becomes impossible. To actively neutralize these confounding variables, behavior analysts use single-subject experimental designs. Simple pre-test and post-test designs are flawed. Taking a measurement, applying a treatment, and measuring again only proves that a change happened after the intervention. It does not prove the intervention caused it. Look at this single subject graph. It demonstrates the reversal, or ABAB design. The y-axis tracks the dependent variable, the target behavior rate. The x-axis tracks sessions over time. We begin by plotting the current behavior in the absence of the intervention. This stable data path is our baseline, phase A. This establishes the first step of baseline logic, prediction. If the environment remains completely unchanged, we predict the behavior will continue along this exact path. Next, we introduce the independent variable. The data shifts down, showing a decrease in the target behavior. But this initial change is only the beginning of proof. A confounding variable could still be responsible. To rule that out, we execute the verification step. We actively withdraw the intervention. The behavior returns to the original baseline levels, verifying that our initial prediction was accurate. Finally, we execute replication. We reintroduce the independent variable. The behavior decreases again, perfectly matching the first intervention phase. We have demonstrated reliable, repeated experimental control. By demonstrating prediction, verification, and replication, the clinician visualizes undeniable proof that the independent variable, and only that variable, is responsible for the change in behavior. The most dangerous professional pitfall in any science is assuming that because a metric improved after an intervention was applied, the intervention caused the improvement. Correlation simply means two variables change at the same time. Causation means one variable directly dictates the change in the other. True causation requires strict criteria. You must select an objective dependent variable and execute the independent variable with high treatment integrity. Neutralize all environmental confounds and demonstrate baseline logic. When all these conditions are met simultaneously, the analyst establishes a functional relation. The ability to empirically verify a functional relation defines applied behavior analysis as a hard science. It guarantees that clinical interventions rely on verifiable control of the environment, yielding measurable, objective improvements in human behavior.